A tank engine consumes thousands of liters of air per minute. It also produces exhaust gases hot enough to boil water. The crew inside needs a constant supply of breathable air to survive. None of these requirements change when the tank drives off a riverbank and disappears completely beneath the surface. The engine keeps running. The crew keeps breathing. The cannon stays loaded. 40 tons of steel moving across a riverbed in total darkness with no access to the atmosphere above. Armies have been doing this since the Second World War. And what happens to the crew if the engine stalls at the bottom is exactly as bad as it sounds. The reason a 40-ton tank does not float is the same reason it can drive underwater. There is no buoyancy to overcome. A tank is so dense relative to its volume that it sinks immediately, settling onto the riverbed under its own weight with the same ground pressure it exerts on dry land. The tracks grip the bottom. The drivetrain functions exactly as it does on the surface. The vehicle does not swim. It simply drives. The problem was never propulsion. It was keeping an internal combustion engine and a human crew alive inside a sealed steel box submerged in water with no access to outside air. An internal combustion engine requires a continuous and massive volume of air to function. A tank's diesel engine can consume well over 1,000 liters of air per minute under load. That air must enter the engine, combust with diesel fuel, and exit as exhaust. On the surface, this is trivial. Air enters through intakes. Exhaust exits through pipes. Submerge the vehicle, and both paths flood instantly. Water enters the intake. As exhaust cannot exit against the hydrostatic pressure of the river above it. The engine drowns in seconds. The crew faces the same problem in parallel. A sealed crew compartment with 3 or 4 occupants consumes oxygen and produces carbon dioxide. On the surface, ventilation handles this passively. Underwater, the compartment is airtight. Without a fresh air supply, the crew begins to suffocate within minutes. The vehicle must solve both problems simultaneously, provide thousands of liters of air per minute to the engine and a continuous breathable supply to the crew, all while the hull is completely submerged. The solution is mechanically simple and operationally terrifying. A single tube, called a snorkel, extends from the top of the tank above the water surface. This tube is the only connection between the submerged vehicle and the atmosphere. The engine draws intake air down through the snorkel, and a separate channel feeds breathable air into the crew compartment. Exhaust gases are routed through a sealed pipe that exits underwater, using the engine's own back pressure to force gases out against the water column. In some designs, exhaust simply bubbles to the surface behind the vehicle. In others, it is routed upward through a dedicated trunk alongside the intake. But air is only half the engineering. The other half is sealing. Every opening on the tank's hull, turret and engine deck must be made watertight before the vehicle enters the water. The main gun barrel is sealed with a muzzle cover or a rubber plug. The turret ring, where the turret rotates on the hull, and is packed with inflatable seals or greased gaskets. Crew hatches are clamped and sealed with rubber gaskets. Engine deck panels, ventilation louvers, ammunition loading ports, vision block mounts, and even the machine gun ports are individually sealed or covered. On a Soviet T-72, the crew can prepare the tank for deep fording in approximately 20 minutes using onboard equipment. Every seal must hold against water pressure at up to 5 meters of depth. The design philosophy diverges sharply between NATO and Soviet doctrine, and that divergence reveals what each military considered acceptable risk. NATO tanks like the German Leopard 2 use a large diameter snorkel assembled from stackable rings mounted over the commander's hatch. The tube is wide enough for a crew member to climb through. If the tank stalls or becomes stuck underwater, the crew can escape upward through the snorkel to the surface. The trade-off is logistical. The large snorkel components must be transported by support vehicles and brought to the crossing site. Assembly takes longer. The system limits fording depth to approximately 3 meters. Soviet engineers made a different calculation. Russian snorkels are narrow tubes only a few inches in diameter. They can be carried strapped to the tank itself and erected in minutes without support vehicles. This makes the crossing faster to prepare and independent of logistics. But a tube that narrow cannot serve as an escape route. If the tank stalls, if the engine floods, if a track throws or the vehicle bogs in soft riverbed sediment, the crew cannot exit. They sit sealed in a dark compartment on the river bottom, breathing whatever air remains in the snorkel, waiting for a recovery vehicle to attach a tow cable and drag them back to shore. Underwater crossings are, by all accounts, deeply unpopular with Soviet and Russian tank crews. The engineering works. The human experience is another matter entirely. The crossing itself is a carefully controlled operation that leaves almost nothing to chance. Engineers survey the river in advance, measuring depth, current speed, bottom composition, and bank angles on both sides. The depth cannot exceed 5 meters. The current cannot exceed 2 meters per second. The riverbed must be firm, sand or gravel, not mud that would bog the tracks. Entry and exit banks cannot exceed 25 degrees. Obstacles, underwater debris, and large rocks are mapped and cleared or marked for avoidance. Approach routes are prepared, and traffic control posts are established on both banks to regulate vehicle flow. This is not an improvised maneuver, it is a deliberate engineering operation. The tanks enter the water one at a time, maintaining 50 meters between vehicles to prevent underwater collisions. The driver cannot see. Water against the vision blocks turns everything dark. Debris and silt cloud any remaining visibility. Navigation is by compass heading. Before entering, each crew is given a crossing azimuth, a fixed compass bearing to maintain throughout the transit. The driver holds the bearing, maintains a constant speed in a single gear, and does not shift or turn. The tank moves in a straight line across the riverbed in near total blindness. The crew communicates by intercom. The engine noise reverberates through the sealed hull. Floating objects occasionally impact the exterior with no warning. The first time a crew does this is described by veterans as one of the most psychologically intense experiences in armored training. The engine is the lifeline. As long as it runs, air flows through the snorkel, the crew can breathe, and the tank can move forward toward the far bank. If the engine stalls, the air supply stops immediately. The crew compartment begins consuming its remaining trapped oxygen. There is no restart procedure that works reliably while submerged. Water pressure against the exhaust ports may prevent the engine from turning over. Even if it does restart, any breach in the sealing system during the stall could have admitted water into the intake or shorted the electrical systems. The standard recovery procedure is not self-rescue. It is extraction by a recovery vehicle positioned on the bank using a tow cable that was attached before the crossing began. Every tank trails a cable for exactly this purpose. The crew waits in darkness until they feel the vehicle moving backward toward the bank. Doctrine specifies that a recovery team must be positioned and ready before any tank enters the water. The technology has roots in the Second World War. Germany developed underwater fording capability for the Tiger tank, which could cross up to 4 meters of water using an extended snorkel tube mounted over the commander's hatch and rubber gaskets sealing every hull opening. The original purpose was Operation Sea Lion, the planned amphibious invasion of Britain, which envisioned tanks driving across the English Channel seabed from barges to the shore. The invasion was cancelled. The technology survived. The British developed deep wading kits for Churchill and Sherman tanks used in the 1942 Dieppe raid and the D-Day assault at Normandy. These used tall intake and exhaust ducts extending above the turret, allowing the tank to drive ashore from landing craft in water deeper than the hull. After the war, deep fording became a standard requirement for main battle tanks on both sides of the Iron Curtain. European geography demanded it. The continent is crossed by hundreds of rivers, and in a conflict where bridges would be destroyed in the opening hours, armored forces needed to cross without them. Every major tank design from the 1960s onward incorporated deep fording as a baseline capability. The T-55, T-62, T-72, T-80, T-90, Leopard 2, and M1 Abrams all include provisions for snorkel-equipped underwater transit. The engineering details vary. The operational principle does not. Seal the hull, extend a breathing tube, drive across the bottom. The system has not changed fundamentally in 80 years. The materials are better. The seals are more reliable. Navigation aids have improved. But the core engineering remains identical to what German engineers devised for a cancelled invasion in 1940. A sealed steel box, a single air tube extending above the waterline, and a crew willing to drive blind across a riverbed with no guarantee the engine will keep running. The principle is simple. The experience is not. Tanks were never designed to operate underwater. They were designed to survive it long enough to reach the other side. The hull changed. The compromise never did.